When sampling, we often don't know the underlying population values, in this case, the population mean. Most commonly, that's the reason we may be taking a sample to try to get a feel for where that population mean might be. Now, that doesn't mean we can't use much of what we've been building. We can still rely upon the concept of the central limit theorem that the sampling distribution of sample means is approximately a normal distribution. We can rely on that in much of what we've built thus far. But of course, a couple of the shortcuts we've taken rely upon the concept of knowing the population mean. It's how we've quickly gotten to where that normal distribution lies, right? We've said the mean of the sample means is equal to the population mean. But if we don't know the population mean, this is, of course, is going to break down in terms of our ability to use it. Similarly, we won't always know the population standard deviation, and in a similar sense, our way to estimate to build out the sampling distributions standard deviation will also break down here. Now, we have fixes for both of these, or we have ways to handle that. At this time, we're gonna kind of ignore this issue and say we still do know the population standard deviation. Now, again, this is uncommon to actually know this, but the fix for this is much easier than or much more straightforward than this unknown mean. So we'll set that aside for now and just work out how we go about understanding where the population mean is most likely to be, or best guess for it, and then also building in the uncertainty we have here. So we're going to attach uncertainty because at the end of the day, we're never going to know for sure where the population mean is. And oftentimes, we never do in practice. So we take a sample, we could take a few samples. We're never going to know for sure what the population mean is unless, somewhere down the road we take a full census of everybody. We may not ever know where the true population mean is, but we can take a pretty good guess. So what guess are we going to rely upon? Well, when we take a sample, so let's say I take a sample, I have some population that I don't know about. Let's take a sample of say let's sample 100 people just to make the math easier for us. We're going to sample 100 people, and what do we get out of that sample? Well, we get an X bar, right? We get an average of those 100 people. Now let's say the average is we haven't even really set up. Let's say 68 inches. Maybe we're measuring height. Okay, and so we've taken a sample of 100 people on campus, and the height is 68 inches. And so when we turn to thinking about, let's try to smooth that out. It didn't really work. When we turn to thinking about where the population mean might be, our default should be, well, why not guess that it's our sample mean? What is the mean of the population? Without any other information, we might as well guess that it's 68. Okay, so we're going to rely upon the concept that, X bar is probably pretty close to the mean. And so actually taking a best guess or estimating the population mean from our sample mean is very straightforward. We simply guess it's the sample mean. Now, of course, this relies upon the concept that we've taken a good random sample. So if we have questions about that, we should stop here and not actually pursue this sample. But as long as we can comfortably assume that we've taken a good random sample, this is a pretty good guess. Now, again, it's not. We shouldn't delude ourselves into thinking that we hit it right on and that we've got this down and we hit the exact value. Okay, and so because of that, we want to build some level of uncertainty around this. To express the fact that we don't have this right on. This is a sample, and our guess here is dependent upon what sample we've just taken. So to do that, we're going to build what's called a confidence interval. And so the confidence interval is going to rely upon the idea of a sampling error. Right? If we recall back, our sampling error is precisely this, that we're going to miss. Every sample is going to miss by some amount. Right? We never assume that we got it right on. And so where is that sampling error, or how do we conceptualize how large that is? Well, there's a range of possibilities of the sample error. Right? We might have got really close, we might have got really far away, but there's some level of, most of the time we're going to get pretty close, sometimes we're going to get further away. Right? We can build that out in a quick, here's the distribution of all the sample means. Of course, we just took one sample. It might have been below, it might have been above, it might have been right next to it, but we don't know which sample we've taken here. Okay, so that's another important thing to keep in mind here, is when we take a sample, we've simply taken a sample that says 68, but we don't know where the true mean is. Okay, so rather than think about it on one distribution, the true distribution might look like this, right? The actual value could be here, and in that case, we're a ways below the actual population mean. We could have hit it pretty close, in which the true mean is pretty close to our 68, and of course we could have. It could be way down there. We could be way overshooting. It could be, 52 or something. So we don't actually know which of these distributions we're sitting on. We just have one sample. We don't know what the sampling distribution is. So that's kind of an aside to how we're actually going to build this confidence interval, but I do think it's important to realize there is a lot of uncertainty here. And that's why we have to go through this process. So the x bar minus mu, of course, we've seen this pop up time and time again, and it's part of our z calculation. Right, and let's put it in terms of sampling. And so this formula we're going to continue to work with. And in fact, when we think about building out the confidence interval, all we're going to do is kind of rearrange this formula. So I'm going to multiply up here by sigma square root of n. And so I'm left with z sigma square root of n as kind of this size, this range calculation. Okay, so we can adjust z for a percentage, and then we have the sigma over square root of n, which captures our standard deviation size of the sampling. Okay, and so what we're left here is x bar minus mu, which again is this measure of sampling error. Okay, and so how we're going to actually use the confidence interval is we're going to say, again, what are we trying to do? We're going to say, hey, what's the mean? Well, we think it's x bar, but it's x bar plus or minus this kind of range calculation. Okay, so we're saying x bar is a good guess, but let me say it, plus or minus this distance here, and this is our confidence interval. So when we already have the x bar solved here for this case. We've said it's 68. Now let's build out the rest of this confidence interval. So z, where is z coming from? Z is simply the level of confidence we want, and it falls directly from the z table. So we can choose what level of confidence we want. Do we want an 80% confidence interval, 90, a 95% confidence interval, a 62% confidence interval? We can pick any level. Now, what's typically done are, the levels of 90, 95, or 99, and most commonly it's 95. So you'll see that most common. So a 95% confidence interval is drawn from the z distribution, and we can think about it in terms of it's really 47.5% on either side, right? Because it's going to double. We want the confidence interval to stretch in both directions, right? We're saying plus or minus, and so we're grabbing both directions. So really, we're looking up 47.5 in the, or 0.475 in the z table, and as you'll get familiar with, so a 95% confidence interval is a z of 1.96. Okay, it's almost the empirical rule, right? This is that little bit refined empirical rule calculation. And so we simply, if we want a 95% confidence interval, we plug in 1.96. If we wanted a 90%, we plug in, you can look this up, but it's 1.645 basically. And each confidence interval is going to have a slightly different value, right? So at 90%, we look up 45% in the z table. Okay, so that's the z. We do need to know sigma and the square root of n. So in this case, we didn't actually say, but we're working under the assumption that we do know the population sigma. So let's just call it 3 here. Okay, just making that up because again, we're working in the assumption that we know it. In future videos, we'll drop that assumption and we'll learn how to deal with it without knowing that. Okay, so we're almost there. So we have z. Let's go back to. So we have. Let's build what we have so far. So we have 68. We think the mean is 68 plus or minus 1.96, and then what do we need? We need sigma, which we set as 3, and the square root of our sample size, which is 100. So this gives us 68 plus or minus, and this is going to be 0.3 times, or 3 over 10, so 0.3. So 0.3 times 1.96 gives us 0.588. Okay, so this is one way to express the confidence interval. We can do, so this is a legitimate way to express that uncertainty, right? So our best guess is at 68, plus or minus, a little over half of an inch. Another way to write it would be to say, so what would that be? 67.412. I've run out of space. I'm going to write it up here. So another way to express that would be 67.412 to 68.588. Okay, so you can express it as just a range in this form as well. So both of those express the uncertainty there, but give us a feel for where we think the population mean is. Again, this is going to change if we change that the confidence interval, right? So this is based on a 95% confidence interval. If we want a 90% confidence interval, all we do is swap out 1.96 for 1.64. Everything else stays the same, but we give a tighter window. That's going to be a smaller window because we're less confident about it. And so we'll play around with this in future videos, but this is the basis for how we build this confidence interval.